Hello everyone, in this talk, we present a dual branches feature interaction-based network, named FINet, for the partial-to-partial point cloud registration. Point cloud registration is a long-standing research problem in the areas of computer vision and computer graphics, and its application scenarios include synthetic, indoor, and outdoor scenes. In this paper, we mainly focus on the first two scenarios. Existed methods can be divided into three categories: traditional methods, deep correspondence matching based, and deep global feature-based methods. Traditional methods can handle the inputs with a small transformation difference and the same shape, while they have three main problems. Taking ICP as an example, first, if the transformation difference between the inputs becomes slightly large, ICP will be easily strapped into the local minima due to the non-convexity. Moreover, the potential partiality of the inputs and the practically existing noise may lead to poor registration precision. Recently, some correspondence matching-based deep learning methods implement descriptors with neural networks to improve performance, and the above problems can be solved to a certain extent. However, most of them have two main issues. Taking RPMNet and Predator as example algorithms, on the one hand, RPMNet relies on the deep features extracted from the local geometric structures. As a result, they can hardly utilize the knowledge of the entire point clouds. On the other hand, although Predator applies a cross-attention mechanism to capture the global picture, it has significant computational and memory requirements. In contrast, global feature-based methods can overcome the above-mentioned issues by aggregating global information without correspondences. Nevertheless, current approaches still suffer two problems. Taking FMR and OMNet as examples, FMR performs poorly in partial-to-partial registration due to the lack of data association. OMNet tackles the partiality by predicting the overlapping mask, which introduces additional computational overhead. In this paper, we mainly focus on these two problems and propose a global feature-based end-to-end method with effective information interaction. Here is an overview of our pipeline. The 3D rigid transformation is represented as the quaternion and 3D translation, which are estimated in an iteratively coarse-to-fine manner. Previously, the correspondence matching-based methods apply a share-weighted encoder to extract features for the calculation of the rotation matrix. The global feature-based methods follow a similar feature extraction process but simultaneously regress the 3D rotation and translation. However, the 3D rotation and 3D translation belong to different solution spaces. Simply adopting factors to balance their weights when computing loss is not a fundamental solution. In this paper, we introduce a dual-branch architecture to split feature extraction, which can obtain a better representation for each of them. Moreover, for partial-to-partial point cloud registration, it is necessary for the network to possess partiality perception ability, which means the feature extraction of the inputs needs the overall information from each other. Therefore, we propose a point-wise feature interaction module, which is inserted in the feature extractor at multiple stages, to enable the information exchange between the source and reference branch, as shown on the left. And a global feature interaction module is adopted after max pooling aggregation to further enhance the data association in the global perspective, as shown on the right. Furthermore, we propose two novel losses to address the remaining issues. Merely separating the 3D rotation and translation branches in the network structure is not enough. It still requires some supervision to ensure that the features extracted from the rotation and translation encoders are sensitive to one while insensitive to the other, and vice versa. Therefore, we propose the transformation sensitivity loss to achieve this goal. Besides, following the previous works, we directly measure the deviation of the estimated quaternion and translation from the ground truth at each iteration. In addition, to avoid the case that the feature extractor only concentrates on the local geometry of the inputs, we design a pointwise feature dropout loss, which encourages the network to learn the global features from more dispersed regions of the inputs. Finally, combining the terms above after n iterations, we have the weighted sum loss, where beta and gamma are weight factors. To demonstrate the effectiveness and robustness of our method, we conduct several experiments on both synthetic and indoor benchmarks. First, we evaluate all the models on the ModelNet 40 dataset, and use the data generation manner proposed by RPMNet. All the learning-based methods are trained and tested on the same categories without noise injected. As shown in the table, our method ranks first in all measures. Note that GO-ICP and DeepGMR are missing since they failed to obtain reasonable results. Then, to evaluate the generalizability, we replace the test set with the unseen categories of the model Net40 dataset and repeat the first experiment. Our method still achieves the best performance in all measures. Besides, to evaluate the robustness against noise, we further repeat the first two experiments. The only difference is that the inputs are jitted by random Gaussian noise. As shown below, our method ranks first in all measures on the unseen shapes with Gaussian noise. Only one metric is slightly worse than Omnet on the unseen categories with Gaussian noise. We observe that the data generation manner proposed by PRNet is different from that of RPMNet. To validate the effectiveness to different partialities, we retrain the learning-based methods on this new partial-to-partial data and repeat the above-mentioned 4 experiments again. Our method outperforms all the other approaches on the unseen shapes with and without Gaussian noise, and the unseen categories with noise while achieving comparable performance compared with Omnet on TS data of the unseen categories. Here, we show some example qualitative results on the model Net40 dataset. A, B and C belong to the unseen shapes, unseen categories, and the most challenging unseen categories with Gaussian noise, respectively. As shown below, compared to several of the latest algorithms, such as RPMNet, RGM, and Omnet, the registration results of our approach perform better in terms of details. We also compare our algorithm with several traditional methods and recently proposed learning-based methods, which mainly focus on the indoor scenario, such as D3 feed and predator. As shown in the figure, our method exhibits robustness to the density variations and obtains relatively better performance with few input points. It is worth noting that although D3 feed and predator achieve higher precision with large inputs, our method is at least 10 times faster than them. We also perform ablation studies to demonstrate the effectiveness of each component, as shown in the table. The dual branches structure is an important feature of our network. Here, we replace it with a single branch structure, where 2 branches are shared weights. For fairness, we double the output channel of each convolution layer of the single branch to obtain a comparable number of parameters to the dual branches. Comparing row 1 with 7, simply applying the dual branches structure only brings a slight improvement without additional supervising. However, only the dual branches structure can enable the ability to learn attentive features and enhance feature interactions. The multi-level feature interaction is another important aspect. We compare the performances in the case of different combinations of the PFI and GFI. Comparing row 1 to 4, we can see that only the PFI improves the performance with a large margin. Since the same encoder is applied for the rotation and translation in the single branch, it may confuse the GFI with their information blended. However, comparing row 7 to 10, both the PFI and GFI improve the performance in the dual branches, and it achieves an extra improvement by combining them. We verify the effectiveness of our point-wise feature dropout loss and transformation sensitivity loss. Comparing row 4 with 6, and row 11 with 12 in Table 3, the point-wise feature dropout loss improves the performance when applying on both the single branch and dual branches. Note that transformation sensitivity loss can only be applied to the dual branches. Comparing row 12 with 13, it improves the performance with the transformation sensitivity loss supervising, which supports the intuition that registration becomes more precise with the rotation and translation features more attentive to themselves, and it exists space difference between them. Furthermore, we train our model with different iterations to show how many iterations are needed. As illustrated in the top figure, the most performance gains are in the first 2 iterations, and n is set to 4 for the trade-off between the speed and the accuracy. In addition, we test the robustness against noise by evaluating our model on the data at different noise levels. Our model achieves comparable performance under various noise levels, which supports that our method is insensitive to the noise. Finally, we test the inference time on the inputs with different numbers of points, as shown in the table, and some settings are listed below. It shows that our method is insensitive to the number of points so that we further test the inference times of each component with more input points. We can find that the inference time is increasing mainly due to the time increment of the encoder since only the computation of point-wise feature extraction increases with the number of input points. We observe that the inference time does not increase rapidly, which may be attributed to the parallel computing capability of the GPU. To better understand the motivation of our designs and accumulate some insights, we make the following discussions. We first try to answer why estimating the saliency points is better. We assume that directly regressing the translation implements two steps implicitly. First, estimate the saliency points for the inputs, then compute the difference between them as translation. It may exist a large rotation gap between the inputs, so it is difficult to regress the translation directly, while regressing SP helps to reduce learning difficulty. At earlier iterations, the transformation difference between the inputs may be still very large, so it requires the saliency points to be the rotation centers, while they only need to be corresponding to each other at later iterations. To explore the partiality perceptual ability of our method, we first calculate the distances between the global features of the inputs in three cases. It tries to extract the same features for the inputs with the interaction, which is however perturbed by the partiality, as shown in B, D. With the feature interaction, the network learns how to utilize the partiality information to better register with the feature interaction, resulting in a larger distance between the global features, as shown in F. In contrast to the intuition that concentrating on the overlapping regions, some of the non-overlapping points also have contributions, as shown in E. Finally, we show the attentive areas of the global features with and without the feature interaction, where the colors denote different iterations. The areas are almost the same without the feature interaction, which reflects the lack of partiality perception, as shown in G. With the data association, the network tends to focus on distinct areas at each iteration, as shown in H. As we use the pointwise feature interaction module in our dual-branch feature encoder, the feature interaction can be applied in two manners. One is the interaction between the rotation and translation branches of the same input. We denote it as self-interaction, and the other is the interaction between the source and reference inputs of the same branch. We denote it as cross-interaction. As shown in the table, all combinations improve the performance. However, it lacks data association between the inputs when only using the self-interaction, resulting in the loss of partiality perception. We can find that the performance of cross-manner outperforms other combinations. Since we use a dual branches structure to extract features and regress quaternion and translation separately, the input of the regression network has several combinations. As shown in the table, we empirically find that both the rotation and translation branches can benefit from the features exchange between each other. In summary, our contributions are threefold. First, we propose a multi-level feature interaction module, which promotes the data association between the inputs and shows state-of-the-art performances on several partially visible datasets. Moreover, we propose a dual branches structure to mitigate the effect of solution space disparity between rotation and translation, so as to further enhance feature interactions. Furthermore, we design a transformation sensitivity loss, which guides the network to learn rotation and translation attentive features. Besides, we propose a pointwise feature dropout loss to facilitate the learning of global information. Here, we show more qualitative results on both synthetic and indoor scenarios. Thank you.